What's going on, guys? Justin here, and welcome back to our sixth example video following our course on differential equations. Today's video is going to be on transforming differential equations into exact differential equations using integrating factors. And with the intro out of the way, let's get into the video. Alright, for today's video, the definition is going to be the same as the previous video. We have the following definition for exactness. So if we suppose m and n are continuous and have continuous partial derivatives, m sub y and n sub x, on some open rectangle R, then we will say that the equation m of xy dx plus n of xy dy equals 0 is exact on R if and only if m sub y of xy is equal to n sub x of xy for all xy on R. So like I said, just the same definition as the previous video. I figured I'd go over it just one more time before we get into our examples. So in our previous videos, we've gone over the concept of an integrating factor. In this video, we're going to use it as a tool to transform an equation into an exact equation. So to rephrase the question, if we multiply by negative 1 over x squared, is the new equation going to be exact? So recall we have the following equality for exactness. We have that the partial of m with respect to y must be equal to the partial of n with respect to x, where m is equal to the coefficient of the dx here, and n is the coefficient of the dy there. So I'm not going to need to write out our partial derivatives to see that this equation currently is not exact, as if you take the derivative with respect to y of y, you'll get 1. If you take the derivative with respect to negative x of x, you will get negative 1, and 1 is obviously not equal to negative 1. So let's go ahead and multiply this differential equation by the suggested integrating factor to see if it is in fact valid. So multiplying this by negative 1 over x squared, we will get negative y over x squared dx. And then those minuses are going to cancel out, so we'll be left with a plus, and the x will cancel the power in the denominator there, so we will just get 1 over x dy is equal to 0. So let's go ahead and see if this new differential equation satisfies this condition here for exactness. So let's start by taking the partial derivative with respect to y of this m term here. So we can see that if we take the partial derivative with respect to y of that, we are going to get simply 1 over x squared. And the question is, does that equal the partial derivative with respect to x of this n term here? But we can see if we take the derivative of with respect to x of 1 over x, we will get 1 over x squared. Since those two are equal, we have indeed created an exact differential equation, which means that negative 1 over x squared is in fact an integrating factor for this differential equation. So now that we've kind of reviewed this concept of integrating factors and applied it to transform an equation into an exact equation, let's get into an example where we use that. So for number 2, we're going to want to solve this differential equation here. We have 2xy cubed minus 2x cubed y cubed minus 4x y squared plus 2x dx plus 3x squared y squared plus 4y dy is equal to 0. So let's start by taking our partial derivatives to confirm that this equation is in fact not exact. So starting with our m right here, we will take the partial with respect to y of that. So we'll have m sub y is equal to, so let's see, for that first term we will get 6xy squared, and that's going to be minus 6x cubed y squared. And then we're going to get minus 8xy, and that 2x term will disappear as there's no y there. And then we will be taking the derivative with respect to x of our n right here. So that will give us, for our n sub x, we will have 6xy squared. And then that 4y will also disappear for similar reasons to before. And obviously these two are not equal, which means we are going to need some integrating factor here. Now there's quite a few different ways you could go about finding integrating factors for differential equations, but right now I want to focus on two specific ones as it applies to this problem. So the two cases we want to check for are, number 1 is m sub y minus n sub x over n independent of y. And similarly, our second condition we're going to check is n sub x minus m sub y over m independent of x. So let's begin by checking to see if this first condition is true. So we can see if we subtract n sub x from m sub y, that first term will cancel, so we'll be left with negative 6x cubed y squared minus 8xy, and that's going to be over our n. So let's check and see what that was real quick. That was 3x squared y squared plus 4y. So we have 3x squared y squared plus 4y. And we can see that if we factor out a y from our numerator there, we will have a nice cancellation, which will leave us with just negative 2x, which is of course independent of y, which means that our condition 1 is fulfilled for this example. Now that we know this condition is fulfilled, we are going to set p of x equal to our result here, which is of course equal to negative 2x. And the resulting integrating factor for this equation, mu of xy, is going to be equal to e to the power of the integral of p of x in general, but in this specific case it's going to be e to the power of the integral of negative 2x, which is of course equal to e to the negative x squared. I believe in a previous video we used alpha for integrating factors, but for this video we're going to be using mu. So let's go ahead and multiply our differential equation by our integrating factor and then check to see if it is in fact exact now. So multiplying our e to the negative x squared through, we will have 2xy cubed times e to the negative x squared minus 2x cubed y cubed e to the negative x squared minus 4xy squared e to the negative x squared plus 2x e to the negative x squared. And that is our new m. So let's go ahead and solve for m sub y. We're going to find it's very similar to before, as our e to the negative x squared is independent of y. So we will get 6xy squared minus 6x cubed y squared minus 8xy, all times e to the negative x squared. And our new n is going to be equal to 3x squared y squared e to the minus x squared plus 4y e to the minus x squared. And we want to find n sub x. Well, that's going to be a bit trickier than before, as this time our e to the negative x squared term will contribute things. So let's begin by taking the derivative with respect to x of our first term, which we're going to have to do using the product rule. So out front we will have y squared e to the minus x squared, and the derivative of that 3x term is going to be 6x, and that's going to be plus 3x squared y squared times the derivative of our e to the negative x squared term, and the derivative of that is going to be negative 2x times e to the negative x squared. And finally, the derivative of our last term is going to be negative 8xy e to the negative x squared. And we can see that both this m sub y and n sub x are indeed equal, so this equation is now exact, and we have found a proper integrating factor, which means we can proceed with the solution process that we outlined in the previous videos for exact equations. So we will recall that we need to find a function g of xy such that g sub x of xy is equal to our new m, and g sub y of xy is equal to our new n. And generally we want to pick the easier to integrate out of these two equations here. So for this case we will be choosing our equation for our n here, as that will be easier to solve. So we have g sub y of xy is equal to e to the negative x squared times 3x squared y squared plus 4y. So integrating that, we are going to get that g of xy is equal to e to the negative x squared times x squared y cubed plus 2y squared plus some function h of x. Now from here we are going to differentiate both sides of this equation with respect to x in order to solve for this h of x using our equation for m. And I'm not going to go over the simple steps to take the derivative of that right-hand side of the equation, but once you take the derivative you will find that g sub x of xy is equal to e to the negative x squared times the quantity 2xy cubed minus 2x cubed y cubed minus 4xy squared plus h prime of x. And I went ahead and pasted our equation for m here so we can compare the two. So we can see that this means that our h prime of x is going to be equal to 2 times x e to the negative x squared, which of course means we can let h of x equal negative e to the negative x squared. And knowing that, we can write our final implicit solution to this differential equation, which will be e to the negative x squared times y squared times x squared y plus 2 minus 1 is equal to some constant c. So let's go ahead and get into our next example. So for problem number 3, we have 2xy cubed dx plus 3x squared y squared plus x squared y cubed plus 1 dy is equal to 0. Let's go ahead and check the partial derivatives of our m and n to verify that this equation is in fact not exact. So m sub y is going to be equal to 6xy squared. And taking the partial with respect to x of our n is going to give us 6xy squared plus 2xy cubed. And we can see that these are in fact not equal, which means we have to look for an integrating factor. So let's go ahead and see if this equation falls into one of the two cases I outlined earlier. Last time we used the case where we subtracted n sub x from m sub y, but it looks like for this case it might be better to subtract m sub y from n sub x. So if you recall the formula for that, we have n sub x minus m sub y over m. And if that results in something that is independent of x, we can use a similar formula to the one we used before to solve for an integrating factor. So let's go ahead and quickly evaluate this here. Well, we can see that the first two terms contributed by these partials are going to cancel out, which will leave us with a 2xy cubed in the numerator. But the denominator is just m, which is also 2xy cubed, which means we are just going to get 1, and 1 is indeed independent of x, so we're good there. From here, we're going to take q of y to be equal to this 1 here. And with that, our integrating factor mu of xy will be equal to e to the power of the integral of this q of y dy. But since q of y is just 1, that will mean we will have e to the integral of dy, which means that this will be equal to e to the y. So let's go ahead and multiply this differential equation by our integrating factor we just found, which is just e to the y. So multiplying our original equation by e to the y will give us 2xy cubed e to the y dx plus 3x squared y squared plus x squared y cubed plus 1 times e to the y dy is equal to 0. So let's go ahead and verify that this equation is in fact now exact. And if it is, we will know that we've selected our integrating factor properly. So our partial with respect to y of our m sub y is going to be equal to, well, let's see, we're going to have to use the product rule on this. So taking the derivative of our first y term, we will get 6xy squared times e to the y, and that's going to be plus 2xy cubed times e to the y again. Let's see if that's equal to our n sub x, and that's going to be equal to 6xy squared times e to the y plus 2xy cubed times e to the y. And these two are, of course, exactly identical, so we're good. So we can proceed with our solution process for solving exact differential equations. So once again, we want a g of xy such that g sub x of xy is equal to our m, and g sub y of xy is equal to our n. This time, let's use the equation for our m, because our m is simpler to integrate this time. So we will have g sub x of xy is equal to 2xy cubed e to the y. So let's go ahead and take the antiderivative of both sides. We will get g of xy is equal to, let's see, we'll get x squared y cubed times e to the y plus h of y, some function of just y. From here, we are going to take the derivative with respect to y and then use this equation here to solve for our h of y to get our final answer. So taking the derivative with respect to y on both sides here, we will get that g sub y of xy is equal to 3x squared y squared e to the y plus x squared y cubed e to the y plus h prime of y. And let's go ahead and recall our n now so that we can compare the two. So n is equal to 3x squared y squared plus x squared y cubed plus 1 times e to the y. This means, of course, that our h prime of y is simply equal to e to the y, which means we can let h of y also equal e to the y, as the derivative of e to the y is itself, which means we can very simply write out our implicit solution to this differential equation, which will be x squared y cubed plus 1 times e to the y is equal to some constant c. So for our last problem, problem number 4, we are just going to convert this differential equation y prime equals x times y squared minus y all over x into an exact differential equation. And we are going to be doing this using the third trick that was used in the differential equations lecture number 6 that Michael went over. I'm going to write it out in a slightly different way, but the trick should be exactly the same. So let's begin by moving some variables around so we can write this in the form that we like to work with when it comes to these types of differential equations. So let's begin by multiplying by x. So we'll get x times y prime is equal to xy squared minus y. And then we can move these terms over by adding and subtracting them, which will give us y minus xy squared plus x times y prime is equal to 0. And from there we can finish rewriting it as y times 1 minus xy dx plus x times dy is equal to 0. So our condition for this trick is, so I'll just kind of put a 3 here. This is the third trick covered in the lecture. So the condition we're going to be looking at for this problem is if m is equal to y times some function of x times y, and n is equal to x times some different function of x times y. And if we have that these two conditions are met, we can solve for our integrating factor, and our integrating factor in these conditions will be mu of xy is equal to 1 over x times m minus y times n. And so we can see that in this particular example, our f of x times y is equal to 1 minus x times y, and our g of x times y is simply going to be equal to 1. So let's go ahead and plug our m and our n into this formula for our integrating factor. So we'll have that mu of xy is equal to 1 over, well, let's see, we will have x times our m, which was y times 1 minus xy. And that's going to be minus y times our n, but our n is just x, so that will be minus xy. So let's simplify our denominator a little bit, and we can distribute that x times y through xy minus x squared y squared minus xy. But those xy's are going to cancel out, which will just leave us with the integrating factor negative 1 over xy squared. And the last thing we will do with this problem is multiply by that integrating factor and then show that this equation is now exact. So if we multiply by negative 1 over x times y quantity squared into our original equation, that will be times y times 1 minus xy dx plus negative 1 over x times y quantity squared times x dy, and that's equal to 0. So on this right side, we can see this x will just cancel out a power in the denominator, so that will contribute a negative 1 over x times y squared. But we're going to have to do a little more work on this left-hand side. So rewriting this as one fraction, we will have xy squared minus y over xy squared. And we can split this up into two fractions. The first one will give us a 1 over x, and the second one will give us a negative 1 over x squared y. So this will be our new m, and that's going to be minus our new n, which will just be dy over xy squared, and that's going to be equal to 0. So let's go ahead and take our partial derivatives to prove that this is in fact exact now. So m sub y is going to be equal to, well, let's see, that first term is just going to go away, and the second term is going to be equal to, well, the negatives will cancel out when we take the derivative, so we will be left with 1 over x squared y squared, and then n sub x is going to be equal to, well, similarly, the negatives will cancel, and we'll be left with 1 over x squared y squared. So these two are equal now, which means our equation has been transformed into an exact equation. And if you want to, you can go about solving it for homework. But that's all we're going to do for this last problem, and that's a good place to stop.